I hope you have understood the earlier 3 rules that I have posted as recordings. If you have any doubt in that, you can ask me quickly, otherwise I will start new topic. So anybody would like to discuss something? Shall I move ahead? So 3 lectures I think were posted. First was on Hebbian learning rule. The second was perceptron, and third was delta. So you can listen to those videos again if you wish. If you have understood, we can move ahead. So in short, what was delta learning rule? It was for change in weight equal to COX, okay, where C stands for learning constant, O is output of the neuron, and X is input to the neuron. So this is the structure, this is output, and these are all inputs, so that we call as X. So the weights associated here, we call it as W vector. So in general, W new is equal to W old plus delta W. So this is a general way of changing weights of any neuron. So this delta W change in weight depends on which learning rule you are using. Okay, so suppose I am using Hebbian, then my changing rule is COX. So Hebbian is unsupervised. That means there is no teacher to teach you. Okay, you will learn on your own. You means your neuron will learn on its own. So it is called as unsupervised. So basically, there is no teacher signal available. And when you go to perceptron, this change in weight is equal to C into D minus O into X. Okay, so this C stands for again learning constant, which we keep very small, maybe in the range like 0 plus to 1, maybe 0.1, 0.2 or so. So we keep a small number here as learning constant. So why to choose a small number? What is effect if I choose a big number? That we will see in subsequent classes. So this C controls the learning. So this thing you can keep in mind, that if I do change in weight from say this position W1, if my weights are changing to new position W2, I can move maybe this much in this direction, I can move this much or up to this point. So these steps I can control using C. Okay, so it is user defined parameter. So in perceptron, this D is the desired response of neuron. So when I supply you neuron like this, I give some input and I expect that it should produce +1. So this is called as teacher signal or supervised learning signal, which I expect from a neuron. And by chance your neuron is suppose giving you -1, then you want +1. So it is giving you wrong answer. So in that case, these weights are updated to produce required result. Okay, so this learning signal, that is desired response signal, controls your learning. Suppose you want -1 and you obtain -1. So D minus O, you can see this is D minus O. O is also -1. So this complete thing becomes -1 into -1, so +1. So there won't be any learning, because whatever is produced by neuron is the required thing. Same is the case when you want +1 and your neuron is producing +1. So +1 minus +1. So this will be again 0. So there won't be any learning. So whenever there is correct output, so when D is equal to O, there won't be any delta W. There won't be any change in weight. So when there will be change in weight, whenever D is not equal to O. Okay. So that time you will see that there will some learning. So this perceptron basic rule is used for the job of classification. So perceptron is for classification. Hebbian is used for memory networks. Okay, and delta is a modified version of perceptron based on gradient based learning. So this change in weight is C into D minus O into F dash of net into X. So this extra term is appearing here. So there is a small change if you compare perceptron and delta. So what is that small change? The small change is just F dash. Now why this F dash is appearing? So you can go for the derivation that was given to you in earlier class. If you don't understand that, then we can discuss. But basically you don't speak, so I can keep on moving. Anybody has difficulty? So obviously nobody will speak, so we can move ahead. Okay. So this is the situation. So these three things were covered in earlier videos, and I hope you have gone through those videos. If you have not gone through those videos, just go ahead to the classroom. They are available there. You can click on them and complete your assignment. So those who have not completed, they will be getting 0 score. Those who have completed, they will get 1 score. I hope you understand the importance of that. Now, before I move to the next set of rules, I want to discuss with you the types of activation functions used in neural networks. So neural network, if I take a single neuron, as you know, the structure is similar for all the networks. Working is very similar. So here lie these weights. So these are my weights, and these are all inputs. Okay, so these are all inputs, and here the main thing lie is f of net, that is called as activation function. So this node is for activation function. So what I do, I take this x1, I multiply with w1, then I take x2, I multiply with w2, and so on up to xn wn. So this total sum is called as net of the neuron. The input net, this at this location, there will be a net input going to this activation function. So what activation function will do, it will take this net value and it will produce some output. Based on this total net value, it will give you some response or output, which is of our interest. Okay, so depending on the activation function, the behavior of neuron will change. So there are many types of activation functions. They are used in practice, and I have listed few of them which are regularly used. The first one is called as linear activation function. So what is linear? Linear activation function says that output is equal to just net value. So whatever is net, that is your output. Or in short, I can write f of net equal to net. So this side of the graph is x-axis is net value and this side is output. Suppose my net value is 0, output is 0. If my net value is 2, output is 2. If my net value is 8, my output is 8. Okay, like that. Whatever is net going to a neuron, say this is my neuron and net value here is suppose 8, then output is 8. So there is no change in the output. Whatever is the sum, that is my output. So this type of activation function is very helpful in a few of the circuits, like your estimation circuits where you estimate certain values. Okay, so there may not be a minimum say like 0 and maximum like 1 or thresholding kind of thing. You want to predict values in a complete range, maybe say from theoretically from minus infinity to plus infinity. Okay, so that is your job. Then you need such kind of activation function, because to this side you can go up to minus infinity and to this side you can go up to plus infinity. Okay, so there is no lower bound or upper bound to this activation function. So we are in need of such functions in the circuits which predict some values. Okay. Predict some values like function estimation. In those cases, I require to have such kind of linear activation function. So more details we will come to know when we will see multi-layer circuits. Right now, you just see that this is a required thing in many circuits. Even in your deep networks, this is required. So there is next type. So this second one, this is called as threshold function. So you produce some output. So this is your output, which is 1 or 0. So output is 1 or 0. There are only two steps. So it is a threshold function which produces 1 whenever your net value is greater than some threshold. Now suppose threshold is equal to 0 in this case. So this is my 0. So whenever your net value is more than 0 or equal to 0, you will see that you are producing 1. Okay, so this is 1. Otherwise, when your net value is less than 0, then you are producing 0. Now suppose I take threshold equal to suppose 5, then what happens? See, this is your net, this is output, and say this is 1, 2, 3, 4, 5, and here onwards you will get plus 1 as your output, and from this point, that is below this threshold t equal to 5, you will see that your output is 0. Okay, so this is a threshold function basically used in classification. Okay, so if certain class, say class 1, is suppose represented by plus 1, and class 2 is represented by say 0. So whenever input pattern say X belongs to class 1, your output will be plus 1. Whenever your input X belongs to class 2, output will be 0. Okay, so this is the use of this threshold function. So we have one more type, one more type of this threshold function. So this is a threshold function which is having drastic change here, 0 or 1, and this is the smooth version of that, that is called as sigmoid activation function or logistic activation function. So there is a transition from 0 to 1, not abruptly, so it will be a smooth transition. Okay, so this will be a smooth transition from 0 to 1. So your output here will be in the range 0 to 1. So depending on net, if net is more than say 0, you will start getting positive output, and when your net is less than 0, you will start getting negative output. The function which does this is called as sigmoidal activation function or logistic activation function. So you can say this is a brother of this earlier word, activation function, say 0 to 1. So instead of that, you have a smooth version, and remember this threshold here is at 0. So if I want to draw equivalent, I should draw like this. So anything beyond 0, in earlier version it produces 1. Anything less than 0, it produces 0. So in this case, there will be a smooth transition from 0 to 1. So depending on this slope constant, I can modify this activation function like this. Say O is equal to 1 plus e to the power minus lambda into net. So if I modify this equation, say number 1 as number 2, what happens? This lambda controls the slope of this function. How fast this function changes value from 0 to 1. If you have say larger value of lambda, then this will be converted into a step function like this. Okay, if you have small value of lambda, then it will move in a sluggish way from 0 to 1, like this. So there is a normal practice that this lambda we keep it equal to 1. So there won't be any headache in say setting the neural network. We have to set so many parameters, so we don't want one more parameter to play with. So directly we can put lambda equal to 1 and we can land to this equation. Okay, so this is S-shaped function. So output is in the range 0 to 1, which looks very similar to the probability, because probability is also in the range 0 to 1. So therefore it is used for models where we need to predict the probability as output. So there are some problems where you want output in the range 0 to 1, which is resembling to the probability. So we basically use this logistic activation function. The beauty of this activation function is that it is differentiable. It is differentiable. That means we can find out slope of the sigmoid curve. Now if you go back and see this delta learning rule, you will see that there is a term f dash. So this term f dash is the derivative of activation function. So delta learning rule has a limitation that you cannot use activation function which is not differentiable. So you must use the activation function which is differentiable. So this logistic function is differentiable, so we can use in delta learning rule. Similarly, linear activation function is also differentiable. If I differentiate this f of net with respect to net, so f dash of net with respect to net, so it will be 1. So since this is differentiable, I can use this linear activation function even in case of a delta learning rule. So remember this point. Now next one is the fourth one in the series, is called as tangent function or hyperbolic tangent activation function. So it is derived or found out from the basic logistic function. So what we do, we take this logistic function which is in the range say 0 to 1, so this is range 1, this is my net. So I multiply this signal by 2. So I increase this by 2 and subtract 1 from it. So if I multiply this by 2, so this is the scaled version, magnified version, and if I subtract minus 1 from this signal, so there will be a DC shift in the negative direction and my signal will look like this. Okay, so this will be net, so this will be plus 1 and this will be minus 1. So same thing you can see mathematically here. So this is actually O into 2 into say sigmoid or logistic function minus 1. Okay, so this sigmoid function, you can see it looks like this, and the modified version of that is the hyperbolic tangent activation function, which is tanh function. It looks like this. So what is the difference between two is that in this case, second case, suppose I write class 1 represented by plus 1, then class say 2 will be represented by minus 1. So that will be the change if I use tanh activation function. So whenever there is a binary class problem, that means there are only two classes to be learned, then this is a better option. So you can go with plus 1 for say pen and minus 1 for duster. I want to learn only two classes, that is pen and duster, then I can use such kind of activation function which is derived from the earlier function, that is logistic function. So this is also heavily used till date in delta learning rule. Okay, and in case of deep networks, still this is a popular activation function in case of this advanced networks till date. Now this is a modified version of linear activation function. It is called as rectified linear unit, ReLU. It's very popular when you learn deep neural networks. So when you see these deep networks, you cannot escape from this ReLU. So what is ReLU? So this was my linear activation function. This is net, this is f of net. So what is done is we are throwing out this portion of my graph. Okay, so this is removed. And we just keep this side linear portion of this curve from 0 onwards. So this portion is removed. It is not there. So what it becomes? So your output is equal to net if net value is greater than equal to 0. It will be 0 if net is less than 0. So this side is 0 and here onwards it is same as whatever is input. Okay, so such modified linear unit is called as rectified linear unit. It looks like your diode. Okay, so diode is a rectifier. You can see that if this is your sine wave and if you pass through a diode, so this will be clipped, this will be removed and only positive thing will be kept. So same way here, all the negative net values are thrown out that are not passed as output, only positive part is coming out. Okay, like this. And this is called as then rectified linear unit. So this ReLU is the most popular activation function right now due to its use in almost all convolutional neural networks or deep learning networks. So you can, in short, you can write this O is equal to max between 0 and net. So this is the way of implementation in your, say, Python or C. You can try this implementation in your practicals. You are going to plot all these curves in your practicals. Okay. Now, a small note is that why it is so popular in deep learning. It solves the problem of gradient, say, dying. You will see that when I use this rectified linear unit, the thing is that I require f dash of activation function, and this you will see when we go for delta learning rule or multi-layers, that this f dash plays a very important role in training hidden layers. Okay, and it is observed that when you have multiple layers like this and you take this first layer, you compute some error, then you, based on that error, you compute a gradient of that error and you pass on that information in backside and change weights here, then you pass on backside, then you pass on backside. So every time f dash of respective thing will be taken into account, and this f dash, which is computed at the last layer, is responsible to change weights in the back side. And it is observed that if you have many layers, this f dash is not sufficient to change weights of the deep layers. Okay, so the gradient is actually dying out when you go in reverse direction with many layers. So there is a problem in deep networks that gradient will die out when your network is really deep. Okay, so the key thing is, if you are using this tanh activation function or logistic activation function, then this problem will be there. So people find out the remedy for that in this ReLU activation function. So this ReLU has solved such this vanishing gradient problems. It is basically called as vanishing gradient problem. So why this activation function is popular? Because it can handle this basic problem of vanishing gradient. And this was solved with ReLU, and then this convolution neural network became very popular. Then people have found out some other versions of ReLU. The first one is called as leaky ReLU. So what is done? Instead of passing on 0, so just cut this thing here and just keep this thing is our standard ReLU. Instead of that, they are now passing a small value, maybe 0.1 of net. So some negative portion here is also allowed, and but that negative portion is controlled by multiplying it to -1. Okay, so this is also inspired from ReLU. So this is called as leaky ReLU. A small portion, negative portion, is leaking through the system, so or leaking through that neuron. So it is called as leaky ReLU. Say then people have thought of another version. Why to just put here 0.1? Why not to have a small alpha number here? Say alpha is in the range, say maybe 0 plus to 1. If I put here 1, then it becomes just simple linear activation function, so which is of not use in this domain. So we can put some 0.1, somebody can choose 0.2 or 0.3 and so on. So as per your wish, you can play with this number. So you will have different slopes here for different values of alpha. So this may be 0.1, this may be 0.2. Say alpha equal to like this. Okay. So this is called as parametric rectified linear unit. So if you say linear activation function is the mother of everything, then ReLU, then third one is leaky ReLU, and fourth one is parametric rectified linear unit. Okay, like this you have 4 options. You may design your own, so that is not restricted. So this is an open research area and nobody is perfect till now. So that's why this area is becoming popular. You can have your own research, you can have your own activation functions, you can have your own neurons to your credit if they work and satisfy the requirement. Okay. The last one in this series is called a Softmax activation function. This is used basically as a last layer in deep networks or CNNs. So it is nothing but it's a kind of a normalization procedure, and your output looks like the probabilities in the range 0 to 1. Okay, so if I take, say, suppose there are class 1 output, there is class 2 output, like that there are class 10 output. So there will be one node for each class in output layer of your network, and each layer will produce it, each neuron will produce output representing one class. Suppose I want that my output should tell me what is chance that applied input belongs to class 1. Suppose I say 0.1, then class 2 is 0.3, and so on. Maybe class 10 is 0.1. Okay, so what happens, I want that some of these outputs must be 1, as the probability of events sum is always 1. So I want that these numbers should sum to 1, and then this max number will represent or give me information that this applied input maximally belongs to this category class 2. Suppose this is representing pen, then I say, okay, this input feature X is a pen because its probability is highest in this case. Okay, so this can be done with the help of this Softmax activation. So what is Softmax activation? It is this formula, that's output is equal to e to the power net I that divided by sum of e to the power net j from 1 to n. So what it means that, say, take this example, there are 5 outputs coming from some neural network. Say this is a neural network which produces 5 outputs, and these are the outputs coming from a neural network. Now I want that this will be represented, or this should be represented in the form of probabilities. So what I do, I take this value 1.3, so it is e to the power 1.3 divided by e to the power 1.3 plus e to the power 5.1 plus e to the power 2.2 plus e to the power 0.7 plus e to the power 1.1. Okay, so whatever number it appears here will be entered here. So you can check this at your end whether this is correct or not. Then you will see that this 5.1 is the largest number in this case. Out of 5, this is the largest number. Then it is represented by 0.9, so the largest probability. And you can check that sum of this is equal to 1.0. So it's very similar to the probability. It looks very similar to the probability of an event. So I can say that the applied input X here belongs to class 2 to the extent of 90%, because it is giving me probability of 0.9. So this is the way to convert your neural network output in the form of probabilities, and the way of doing this is called as Softmax. We will choose maximum out of this. So what will be my decision for input? I will go with max. So this is the max term. That's why it is called as Softmax. Okay. So there is hard max also, so which takes just blindly max number of your applied input, say coming out of this network. So I can just pick up this thing and I can solve the problem. But people want that it should be converted like a probability and then decide the things. So we can do that. So it's not hard and fast to use this, but people do use it. So in short, we can say there is a linear activation function, there is a threshold activation function, sigmoid. So this is a linear, this is a threshold, this is a logistic, this is tan H, then this is my ReLU, this is a leaky ReLU. Okay, then I can have parametric ReLU like this. Okay, so there is a Gaussian, so you can use your Gaussian equation as activation function. So output is like this. So this is also used. And then you have Softmax, which is this one. Okay, so you will implement this in your practicals. Let us stop here. If you have any doubt, you can ask. Any doubts? My speaker was off, so I was not able to listen you. So if you have any doubts, you can ask. So you must have received one attendance sheet meanwhile. I hope you have done that attendance.